Determine if the function is even, odd, or neither. F of x equals x to the 11th minus x squared. Determining if a function is even or odd algebraically, by the way, I pulled this from our notes, and I have this set of instructions on a process that we can go through to decide whether our function is even, odd, or neither. And it starts with calculating f of negative x. And once we do that calculation, we're going to compare the calculation to the original function. If that calculation is the same as the original function, then we're going to say that the function is even. And if that calculation is the opposite of the original function, we're going to say that the function is odd. Now, the reason we do this is from the definition of even and odd. We have a definition of f of negative x equals f of x for even. So that's why it's the same. We've got this equals. And then for odd, we have this definition f of negative x equals negative f of x. So that's why we have the opposite, because this equals the negative of f of x, the opposite of f of x. So we are going to calculate f of negative x. So everywhere I see an x, I substitute negative x. We have negative x to the 11th minus negative 11 squared. And here we have negative to an odd power. So that means I have an odd number of negatives. An odd number of negatives is going to be negative. And we still have x to the 11th. I'll carry down this minus sign. And then, I apologize for that. That should be a negative x, not a negative 11. So there we have a negative to an even power, and an even number of negatives will be positive. So that will be x squared. And then we want to compare this answer to f of x. So I'm comparing this calculation to f of x. So when I compare these two, I'm going to ask myself, are they the same? And I can see they're not the same because this one has a negative and this one doesn't. So I can cross being an even function off. And then I want to decide if they are opposites of each other. So if they're opposites of each other, I'm going to be able to factor out a negative from the function. If I factor out a negative from the function, I get negative times x to the 11th plus x squared. So I have here this negative being opposite, but all of this doesn't match our f of x. So it actually does not match the opposite of f of x. So I'm also going to cross being odd off as well. So it's not even, it's not odd, it is neither. So this function is neither even nor odd. On this question, we're given a graph of a function, and we're asked to find the domain and range of the function. So the domain we know is the x's, the range is the y's. We need to state a set of all the x's for the domain, a set of all the y's for the range. But this graph has some interesting features that you may not be familiar with. So I want to point those out to you first. So we notice that on this graph we have these dashed lines that are in a different color, and they don't seem to be actually part of the graph because they're in that different color. So the graph itself is just these red lines that we see here. But these dashed lines seem to be guiding the graph in a way. These dashed lines are what we call asymptotes. We're going to study them in much greater detail when we get to chapter 4, when we discuss rational functions and their graphs. But what we need to know about them, and this is going to help us define the domain and range, what we need to know about them is that these dashed lines are guiding where the line goes. So this arrow that I'm highlighting right here, you can see is very near this dashed line. This dashed line is at x equals -2. And so this arrow is going to follow the pattern where it gets closer and closer to the dashed line without ever reaching it. So we follow this pattern where the arrow is going to continue to go up and to the right, but it's never going to cross over that dashed line. It's always going to just get closer and closer. And the same thing can be said of some of these other arrows. The arrow is going up and to the left here, getting closer and closer to this dashed line, which is at x equals 2, and it will never cross that line. The same thing happens down at these arrows. This one on the left is going down and to the left and will never cross. This one is going down and to the right and will never cross. And then finally we have this horizontal dashed line. So this one would be called a horizontal asymptote. And we have arrows on the end here. And these arrows on the end will get closer and closer to that dashed line without crossing it. So this one is going down and to the right and will never cross the line y equals 5. This is going down and to the left and will never cross y equals 5. So that will be helpful for us in finding the domain and range. So we're going to start with finding the domain. So when I am looking for domain and range on a graph, I like to use a ruler, or if you don't have a ruler, you can use your pencil and hold it vertically. So I'm starting with domain, and the reason why I hold the ruler vertically is because my ruler is pointing to different spots on the x scale. So this is going to help me find the domain because it's pointing to the x. So let me erase those. We're going to be using interval notation with our domain. And interval notation has a lower bound and an upper bound. So the lower bound in this example, because of this arrow here, remember the graph is going to continue the pattern of down and to the left forever because of the arrow. So our lower bound is actually -infinity. So our domain is going to start at -infinity. Our interval notation starts at -infinity. So I start on the left, which is the smallest, and I continue to the right. And I notice that my ruler is continuing to touch the graph all the way over here. So that means all of these x values are included in the domain. Now it's going to continue like that until we get to this arrow and dashed line. So remember what we said that means earlier is that the line will continue to go up and to the right, but it will never cross x equals -2. So it will never reach x equals -2, and that means that -2 is not part of the domain. So I'm going to put an upper bound on my interval at -2 so that we don't include that in our set. Down here, we have this arrow that goes down and to the left. So we know all of the x's that are above -2 are included in the domain. So I need to start my set notation again, my interval notation at -2. So -2 is not in the domain. However, all the numbers that are right above -2 are in the domain. So as I continue to move to the right, we get a similar situation happening at the next asymptote. This arrow down here indicates we're going to go down and to the right. So that means all of the numbers leading up to 2 are in the domain. But since that line never reaches 2, 2 is not in the domain. So we're going to stop that interval at 2. Up here, the arrow continues to go up and to the left, never reaching 2 and x equal 2. So we're going to start our interval at 2. And then the graph continues on all the way this way. So all of these x's are included all the way, and this arrow tells us that it's going to go to infinity. So that's our interval notation. If I were to compare this to a number line, what we're saying is that -2 and 2 are both excluded from the domain. However, all the other real numbers on the number line are part of the domain. So that's how we write the interval notation. -infinity to -2. That's all the numbers that are less than -2. -2 to 2. That's all the numbers in between -2 and 2. And then 2 to infinity, those are all the numbers greater than 2. And I should have a union symbol here as well. So I'm going to get my ruler back out to talk about the range, and I'm going to hold the ruler horizontally when talking about the range, because the range is the set of all y's, and my ruler held horizontally will point to the different y values on this y-axis. So we're going to start from the bottom, which is the smallest y value. And the reason why we start from the bottom is that interval notation is always written smallest to largest. So we want to start with the lowest number. So these two arrows that we see at the bottom indicate that the line will continue to go down and down and down. That means we don't have a starting y value. We don't have a lowest y value. And to indicate that, we write -infinity. So that's our lowest y value, and I'm going to move my ruler up, and we notice that the ruler is touching the graph, so all of these y values will be included in the range until we get to this y value right here. This is now where the line stops, and that y value there is a 0. So our range will stop at 0. And this time, I'm going to use a bracket on the interval notation. Now, the difference between the parenthesis and the bracket in interval notation is parenthesis means that the number is not included, and bracket means that the number is included. So here, we have a point on the graph, and that point on the graph is 0, 0. So 0 should be included in the range. Whereas when we wrote -2 and +2, -2 and +2 were the numbers that were not included in the domain, so we don't want to put brackets on those numbers. So we stopped our range at 0, but I can see pieces of the graph above my ruler, so I know I'm going to have to start my range again. So let's keep moving up to see when we should start that range again. We're going to start the range right when we get to this horizontal asymptote, and that's going to be at 5. So we're going to start our range at 5. And we want to make a decision about whether we're going to include 5 or not, whether we're going to put a parenthesis next to 5 or a bracket next to 5. So remember what we talked about is happening at these arrows on the ends. The line is going to get closer and closer to the dashed line without ever reaching it, without crossing it. So 5 is not included in our range because the graph will never reach 5. The line will never reach 5. So we use a parenthesis there. Let me write that a little bit neater. So then I'll continue moving my ruler up. I can see that my ruler is touching the graph, so all of these y's are included in the range, and those arrows indicate that the graph will continue to go up and up and up forever, meaning that there's no highest y value, and that means that we're going to stop our interval at infinity. I guess it really doesn't stop because infinity means it goes on forever, but that's how we're going to write the notation. So we have the range being from -infinity to 0, including 0, union with 5 to infinity. So the point 0.05, I just got a question, so I'm going to try to answer that. The point 0.05 is right here. And that point is not included on the line. So the graph itself is this line, so we would not include 5 in the range. So on this question, we are given the graph of a function here, and we're asked a couple questions about this graph. We're asked for how many values of x is f of x equal to 3. The one thing we have to keep in mind with this notation is that f of x is the same thing as y. So this is saying that y equals 3. So if we reread the question with that in mind, it says for how many values of x is y equal to 3? Now one way for us to approach this is to consider the equation y equals 3 and the graph of that equation. The graph of y equals 3 is a horizontal line. So I'm going to draw a horizontal line at y equals 3, and it would look like this. So this line, y equals 3, has every single ordered pair on that line has a y-coordinate of 3. We can see that there's only one point on our graph that falls on that horizontal line. So there's only going to be one point on our graph where y is equal to 3. So see the wording in this question? For how many? This is counting how many values of x have a y of 3. So the answer to this is 1. We have one x that has a y of 3. Then in our second part, it says, what is the value of f of 7? So we have to keep in mind what this notation means. This notation is indicating to us that x is equal to 7, and we want to answer with the y value. The y value when x is 7. So when we see that notation f of 7, we need to know that that means what is y when x is 7. So this is something that we're going to read off of the graph. We're going to look for an x of 7, which 1, 2, 3, 4, 5, 6, 7, which would be here. And on the graph, we have one point with an x of 7. That's 7, negative 1, because this line is flat or horizontal along that section. So all of the y values are negative 1 on that section. So we're going to answer f of 7 is equal to negative 1. Find the x-intercepts of the graph of the function without graphing the function. Our function is f of x equals the square root of x plus 16 minus the square root of x minus 2. And we're looking for x-intercepts. The way that we find x-intercepts is to let y equal 0. And so just to back up a little bit, an x-intercept is where the graph crosses or touches the x-axis. And the x-axis will have all of the y-coordinates equal to 0 on the x-axis. So that's why we let y equal to 0. Now in our equation, we don't have a y, we have f of x. And f of x is the same thing as y. So we're going to set f of x equal to 0, and that will lead to this equation. 0 equals the square root of x plus 16 minus the square root of x minus 2. Now to solve this equation, we need to get rid of the radicals. Now these are square roots, and the way you get rid of square roots is to do the opposite, which is to square. But before we do that, we have to have the radical isolated on one side of the equation for it to work. So I'm going to add square root of x and 2 to the other side of the equation so that square root of x plus 16 is isolated on the right. Square root of x plus 2 equals square root of x plus 16. Now I'm going to square both sides. I have square root of x plus 2 squared equals square root of x plus 16 squared. On the right-hand side, we've done opposite operations. The square root and the square cancel each other out, leaving us with x plus 16. But on the left, the square root wasn't isolated. Right? Here we have the square root, and then we have this extra bit. So the square root wasn't isolated. We're not able to cancel out the square root. So we actually have to work out the multiplication with this square. So we're going to work out square root of x plus 2 times square root of x plus 2. And I'll continue that up here. So we're going to multiply the first two together. That's square root of x times square root of x. We'll multiply the outside two together and get 2 square root of x. We'll multiply the inside two together, and that gives 2 square root of x. And we multiply the last two together. 2 times 2 is 4. And I'm going to copy down the right-hand side of the equation, x plus 16. So let's simplify on the left. Square root of x times square root of x is square root of x squared. Here we have 2 square root of x and 2 square root of x. These are what we call like radicals. And like radicals, we can add together just like we can add like terms together. So this has a coefficient of 2, and this has a coefficient of 2, and we're going to add those together and get a coefficient of 4. On the left, we still have square root of x squared. We can simplify that to be x. The rest I'm just copying down. So I was able to get rid of this radical up here by squaring both sides. However, there's still a radical in my equation. So I need to go through that process again. I need to isolate that radical and square both sides to get rid of it. So let's start isolating it. We're going to subtract x and subtract 4 on both sides. That leaves 4 square root of x on the left. And on the right, x minus x is 0. 16 minus 4, that would be 12. I'm still going to isolate the square root of x by dividing by 4. 4 square root of x means 4 times square root of x. So we're getting rid of that 4 with the opposite operation of division. So that leaves me with square root of x equals 3. I'm going to get rid of that square root by squaring both sides. So square root of x squared and 3 squared. The square root and the square cancel each other out, and 3 squared is 9. So that leads us to x equals 9, but we have one more step to go because this operation that we did of squaring both sides, and we did it twice, can sometimes lead to solutions that don't work in the original equation. So we need to check to make sure that this solution of x equals 9 works in this original equation that we started with. So let's check that. So I've got 0 equals the square root of 9 plus 16 minus the square root of 9 minus 2. Square root of 9 plus 16, that's the square root of 25. Square root of 9 is 3. And then square root of 25 is 5. Negative 3 and negative 2 combine to be negative 5. And you can see that 5 minus 5 is 0. And that solution does check out, meaning that it works in the original equation. So x equals 9 is our solution, and the ordered pair 9, 0 would be an x-intercept. Find the x-intercepts and the y-intercept of the function. We have the function f of x equals 2x squared minus 10x minus 3. I'm going to start by finding the y-intercept. It's usually a little bit easier. We can find a y-intercept by letting x equal 0. So let's pause there and say y. The definition of a y-intercept is where the graph crosses or touches the y-axis. The y-axis is that vertical axis, and if we think about all of the ordered pairs that are on the y-axis, all of them have an x-coordinate of 0. So that's why we let x equal 0 to find any y-intercepts. So I'll substitute a 0 into the function, and that will give f of 0 equals 2 times 0 squared minus 10 times 0 minus 3. And 0 squared is 0, times 2 is 0. 10 times 0 is 0. And then if we simplify, we end up getting a negative 3. So this function has a y-intercept at 0, negative 3. So then we want to find our x-intercepts. To find an x-intercept, we're going to let y equal 0. Let's pause for a moment to say why we're doing that. The definition of an x-intercept is that an x-intercept will be at a point where the graph crosses or touches the x-axis. The x-axis is that horizontal axis, and all of the points on that horizontal axis are going to have the y-coordinate being 0. So that's why we set y equal to 0 to find the x-intercept. Now in our equation we don't have a y, but we know that f of x is the same thing as y. So we're going to set f of x equal to 0. That's going to give us this equation, 0 equals 2x squared minus 10x minus 3. This is a quadratic equation, and I want to solve this quadratic equation. Now we have lots of different methods for solving quadratic equations. We have factoring. We have the square root method. We have something called completing the square. And finally, we have the quadratic formula. All of them have good value. I recommend learning them all. But my go-to strategy when I'm trying to solve a quadratic is that I usually start by trying to factor it. I solve by factoring because the answers look a little bit cleaner if we're able to factor it. And then if factoring doesn't work, and factoring doesn't always work with quadratics because not every quadratic can be factored, so sometimes factoring is not going to work. So if it doesn't work, then I go to the quadratic formula. And the quadratic formula is nice because it does work on every single quadratic. Even the ones that can be factored, you can use the quadratic formula. So I'm going to start by trying to factor, and if that doesn't work, we'll use the quadratic formula. So when I'm trying to factor, I usually use the guess and check method. There are other methods for factoring out there. So I'm going to set up two parentheses, and the numbers that go in the front here need to multiply to be 2x squared. Now 2 only has one pair of factors, that's 1 times 2, so I'm going to use 2x and x. Then the numbers that go in the back need to multiply to be this last number. That last number is a 3, and 3 only has one pair of factors, that's 1 times 3. So we're lucky in this example that we have very few choices for factoring, and that can help us figure out if it can factor very quickly. So I'm going to try 3 times 1 like this. And what we need to do is we need to check to see if this guess is correct. And we're going to check by seeing if we get the right middle term. So if I multiply the inside two numbers and the outside two numbers, that's what makes up that middle term. So that would be 3x and 2x. Now 3x and 2x, if we add or subtract those, are not going to give us that middle number of 10. So this guess is not correct. I'm going to try one more guess, and I try that guess by switching this 3 and 1. So I'll put the 1 here and the 3 here. And let's try the middle two numbers now. 1 times x is x, 2x times 3 would be 6x. And if I add or subtract 6x and x, that doesn't make the correct number in the middle. So I've tried every pair possible in every combination, and I didn't get a factorization that works. So I know that factoring is not going to work on this example. So we'll move on, and now we'll try the quadratic formula. So the quadratic formula works in this way. You can take any quadratic equation, which is ax squared plus bx plus c equals 0, and you can solve it with this formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So let me erase where I tried to factor. And in order to use this formula, I need to know a, b, and c. A is the coefficient of the squared term. B is the coefficient of the x term, the linear term. And c is the constant. So we have a being 2, b being negative 10, and c being negative 3. And we're going to substitute these into the quadratic formula. So we're going to get x equals negative. There's a negative in the formula, and b is negative. So that's negative 10 plus or minus the square root of negative 10 squared minus 4 times a, which is 2, times c, which is negative 3, all over 2 times a, and a is 2. Then we're going to simplify using order of operations. So I have negative and negative 10, that's a positive 10. Inside the radical, I'm going to apply the exponent first. Negative 10 squared is 100. I'm going to do the multiplication next. 4 times 2 is 8. 8 times 3 is 24. And I have an even number of negatives, so that's going to be plus. 2 times 2 is 4. And let's continue here. Inside the radical, I have 100 plus 24, that's 124. And then at this point, I want to simplify the radical first as much as I can. So I need to think of the factors of 124. Now I'm sure that there are a lot of factors of 124, but the ones we really care about are the ones that are perfect squares. And the reason why we care about the perfect squares is because we're trying to square root. So we're going to test out 4, which is 2 squared, 9, which is 3 squared, 16, which is 4 squared, and see if we have any of these factors. So I've got my calculator here, and let me divide 124 by 4, and that does work. It's 31. And 31 is prime, so it can't be factored anymore. So I'm going to use 4 times 31 as a factor of 129. So let's rewrite that 124. Let's rewrite that 124 as 4 times 31. Now we can apply the square root to these individual factors, and we get 10 plus or minus square root of 4 is 2, and 31, because it's prime and it's not a perfect square, we're going to have to leave that radical on there. So we get 2 square root of 31. The final thing that we're going to do to simplify is, this is a fraction. We always want to write our fractions in lowest terms. So we're going to look for common factors, and I notice that all of these numbers are even. So that's a factor that we're going to be able to cancel out, a factor of 2. So let's factor a 2 out of the numerator. That would leave 5 plus or minus square root of 31 over 4. And then we're going to be able to cancel a common 2 out. So this is 1 and 2. And we get our answer of 5 plus or minus square root of 31 over 2. Now, I've also seen some sources display this answer in one more way. And what they like to do is, instead of writing this as one big fraction, they like to write it as 2 smaller fractions. If you write it like that, you would have 5 over 2 plus or minus square root of 31 over 2. So either one of these last two are fine. They're in the simplest form. So we have 2 x-intercepts, and the x-intercepts are 5 plus and minus square root of 31 over 2, comma 0. So those are our x-intercepts. And remember earlier we found the y-intercept to be negative 3. Find the x-intercepts and the y-intercepts of the function f of x equals x squared plus x minus 110 over x squared plus 8x. So I'm going to start by finding the y-intercept. And we find a y-intercept by letting x equal 0. So if I substitute a 0 in for this function, that would give me 0 squared plus 0 minus 110 over 0 squared plus 8 times 0. If I simplify, 0 squared is 0, plus 0 is 0, minus 110 will give me a negative 110 in the numerator. And in the denominator, I have 0 squared plus 8 times 0, and that will give me a 0 in the denominator. Now, when you have a 0 in the denominator, this is dividing by 0, and that is an operation that is undefined. So because it's undefined, we know that there is no y-intercept. So there will be no y-intercept for this function. So then I want to find the x-intercept. To find the x-intercept, you're going to let y equal 0. In our equation, we don't have a y, but we know that f of x is the same thing as y. So if I substitute a 0 in for f of x, that'll give me this equation. 0 equals x squared plus x minus 110 over 0 squared plus 8. Excuse me, I'm not plugging in the 0 there. So it should be x squared plus 8x. Now, when you initially look at this equation, it looks pretty complicated, but it actually simplifies very quickly. So this is called a rational equation. And the way that we solve rational equations is to clear the denominator, clear the fractions. And you clear the fractions by multiplying by the denominator on both sides. I'm going to multiply the left-hand side of the equation by x squared plus 8x. And I'll multiply the right-hand side of the equation by x squared plus 8x. Now what this does for us is it clears the denominator, or cancels the denominator. Because we're multiplying and dividing by the same thing, that's a form of 1. So we can cancel that out. And then on the left-hand side, remember we have a 0, and 0 times anything is 0. So we end up with 0 equals x squared plus x minus 110. So then we're going to solve this quadratic, and I believe this one can be factored. I'm going to factor, and that gives me x times x is x squared And 110 is 10 times 11, 10 times 11, and I need a plus on the 11 and a minus on the 10 to factor that correctly. And once we have it factored, we'll set each factor equal to 0 using that zero product property. And we get x equals 10 and x equals negative 11 when we solve those equations. One thing you should check with rational equations is to make sure that these are not restricted values. What I mean by that is if you were to plug in a 10 for x, would that cause the denominator to be 0? And the answer to that is no. So this is an x-intercept. And if we were to plug negative 11 into that denominator, would it give us a 0? And the answer is no. So these are both valid x-intercepts of the function. So we have an x-intercept at 10, 0, and another one at negative 11, 0. On this question, we want to classify the given function as a polynomial function, a rational function, or root function. Then find its domain and write the domain in interval notation. So just real quick, quick and dirty, a root function will have a radical. A rational function will have a variable in the denominator, and the polynomial function will be nice expressions where the exponent is a whole number, 0, 1, 2, 3, and so on. So this one is pretty easy to classify as a root function because we see that variable underneath the radical. So we have a root function, and then we want to find the domain of this root function. And when you're finding the domain of a root function, you need to pay attention to the index. And you need to pay attention to whether the index is even or odd, because with even functions, even roots, the even root of a negative gives you I, which is a complex number. So we don't want to include numbers like that in our domain. However, the odd root of a negative is a real number, and we do want to include those numbers in the domain. So on this example, we have the square root, and the square root has an index of 2. So this one is an even root. So we do have a restriction. We want to avoid having a negative underneath the radical. So to avoid having a negative underneath the radical, we're going to take the expression underneath the radical and set that greater than or equal to 0. So what's underneath the radical needs to be positive or 0, not negative. That's what this inequality does for us, greater than 0. So I'm going to solve this inequality by subtracting 9. I get negative x is greater than or equal to negative 9. Divide both sides by negative 1. When you have an inequality, you need to reverse the inequality symbol anytime you divide by a negative on both sides. So that gives x is less than or equal to 9. This is our domain. These are the values that will produce a positive or 0 underneath the radical. So I'm going to plot that on our real number line. Let me mark a 9. I want to include 9, and I also want to include any numbers that are less than 9. In interval notation, we always write a lower bound and an upper bound for our interval. The lower bound is negative infinity. The upper bound is 9. Infinity will always get a parenthesis next to it, and 9 will get a bracket because that 9 is included in the domain. So this is our domain in interval notation, negative infinity to 9 with 9 included. Thank you for checking out my videos. Have a great day.